Okay. Before I start, I will tell you if anybody interested in research, I can arrange for here. Oh, it's mobile. Doing some kind of the research on nanotechnology. You know what's nanotechnology? Yeah. Huh? Nanotechnology. Okay, is دقائق صغيرة يعني 10 to the minus 9. We made them and then we study the antibacterial activity and anti-cancer activities. Okay, if somebody interested, we can arrange for him. Probably I supervise, but we have to talk to people in the RCSI. Okay.
So you go to RCSI to make the research?
They're coming to there.
Oh, is it like on the weekends or?
Well, we have a choice that we could not weekend. Nobody go on the weekend, and we have a rule over there is you cannot answer your emails in the weekends.
Yeah.
Okay.
So like it's gonna be during the study hours.
But we have if a mid-term holiday, if you can do that, you can come, or you can do summer research. عطلة صيفية okay, or maybe I could make 4 people sitting there as well. Okay, I just huh? What? No, just one 4 people only. Okay. Okay, I really rearranged the lecture, Probably you see it probably different than yours you have, I'll just move a few slides from the middle to the beginning, okay? But this content is the same, and there's no change at all, It's okay. Maybe something extra to explain things better, but the content is the same, Okay? So it will be the last lecture on hemodynamics, Okay? We're going to talk about, for the previous we talk about what? Continuity principle, Bernoulli's, yeah? And what else was? The flow or the things, Reynolds number, okay? Today we talk about Laplace's number and Poiseuille's law, okay? And I say how this thing is applied to the things. So, if you have a tube like this, okay, there is to flow things going from one point to another point, you have to have the pressure differences. And you have a pressure also alongside and then across. Okay? This the one alongside is you got perfusion pressure. That is what pressure is being, say for example, is be higher at this point compared to that one to get blood go to the ends of the limbs of kind of things. That's you got perfusion. And then across we call it what? Transmutal pressure. Okay? So transmutal pressure is responsible for our eyes to not collapse, our heart is not collapse, and also our arteries is not collapsing. Okay? It's a difference between the pressure inside the vessel and the pressure outside the vessel. So that is transmutal pressure. Then we say that is perfusion is the difference between one position here and another position, 2 different locations. This one is pressure inside and pressure outside. So we can define that is the transmutal pressure differences between inside and outside of any structure. In our case, it would be heart, eyes, and vessels, blood vessels. Okay? Okay. So, for example, what is, I've given some example, pressure differences between inside and outside of the left ventricle and pressure inside outside of the blood vessels and pressure inside and outside of the eye. If I have always have to be pressure inside bigger than the pressure in outside to not let the structure collapse. Okay? يعني واحد يقول فقست عينك وش اسمه pressure خراب okay. it could collapse, things. Okay, we say that we have that. So the transmitter pressure is related to the tension of the walls and to radius through the Laplace's law. Okay, so that is related to the what? Tension, some elastic tensions. Elastic means what does elastic mean? Means pulled and coming back. If you're losing elasticity, not coming back. Aneurysm losing elasticity. Okay, so you have that as you can pull those things. Then a rubber band, you have pull it, and at the end you're getting something they never go back to the same position. That is losing elasticity at that point. Okay, so this is the elastic tension related to elastic tension of the noise and the radius of the vessels. And through this simple equation, which is the pressure inside minus pressure outside. Of course, that inside is all bigger. That is, we put it inside first. Okay, tension T and radius R. So if it has a tube like this, okay, so we're going to see that is the pressure differences between this point to this point in here is equal to radius, that we say radius here, consider this the cylindrical shape, okay, and the tension, tangential tension on the surface of the tube or the vessel itself, okay. Now if you say, for example, you can see that is I have a tube like this here, okay, and then there's a probability that we say that is a blood flowing in there. So I have a pressure on the aneurysm, and then I have a tension. So I say the tension, definition of the tension is a force per unit length tangential to the vessel walls. This is a tangential to the walls, not perpendicular or مماس إلى سطح vessel itself, okay. And if you look at that, capillaries, now remember that is when we have arteries, isn't it? Yeah, aorta, arteries, arterioles, capillaries. Yeah, and then when it go down from it's going from large diameter to the small diameters, which is capillaries. So, for example, if aorta is about nearly, if I don't take the number right, it's 25 millimeters, something like this. And then arteries would be about 3 to 5 millimeters in here. When you go to capillaries, in microns. Okay? So that is the big differences in the R of the things. Now, if you look at that one, we have two equations here. One of them, see tension equal to pressure radius. And then for spherical ones, I have divided by 2. Okay, so the tension on the thing, on the spherical ones, is always less than the cylindrical ones. The reason is we explain later on why is that. So capillaries of very low pressure needed. So for example, that we take that one. If this, we know that is the pressure inside the capillaries is very small. Okay, remember this graph is go down, isn't it? Yeah? And I ask you which was the more drop in the blood. Yeah? It's coming out capillary. Pressure is very low and radius is small. These two things make what the tension in the capillary is very small.
These cause aneurysms?
No, that is, just hold on a moment, okay? This is pressure low, radius low, tension is low. So it doesn't need very thick walls for the capillaries. In other words, we don't need very high tension, okay? But you will say that is the, if say for example in an artery or the capillaries or the things, I mean, if you increase in the pressure, so what does happening increase the pressure means that is you increase the tension of the thing. Say for example, increasing the pressure in here, increasing the tension also. When this is, when I say is losing elasticity, you're getting what? Aneurysm. And we explain how we explain physics of the aneurysm, isn't it? Yeah? We say it what? We said continuity principle, isn't it? Yeah? We define aneurysm as what? Widening of the blood vessel, become big. okay, large. You're losing elasticity. When it becomes large, it means what? Radius is getting bigger. When radius is bigger, cross-sectional area is getting bigger. So velocity is go down according what? Continuity principle. Yeah? Remember continuity principle, we say Q equal to AV, isn't it? Yeah? So cross-section and velocity, they are inversely proportional. When a cross-section is getting bigger, velocities go down. Okay. When velocities go down, according to Bernoulli principle, remember P plus V equal constant, yeah? Then the pressure is increases to keep constant. And number I told you that is if you have 10, you make a 4, have to be 6, the other one is 6 and make a 4, the other one will be 6, okay? So keep the constant. So according to continuity principle, cross-sectional area getting bigger, velocities go down. According to Bernoulli principle, what is happening? Velocities go down, pressure increases. According to Laplace's here, when the pressure increases, means tension is increases. Okay, when tension increases, it means that already you have a weak, isn't it? Yeah. So is the possibility could be rupture? Huh? Proportional to the you can write it down, take it once. Yeah, this maybe yes, yeah, okay. So this would be things, So if you're getting pressure high, T is getting high, and then it could be rupture in here. Okay, you understand how physics, how we can getting things together. I mean, a lot of the people think is that physics is not. I'm doing medicine. I don't need physics. I mean, all of you. That's just why you don't see people here. You have to believe in it. If you're driving your car in the desert, there's nobody there. If you do a mechanic of the car, how you're fixing the car, you will trust in yourself more.
It also makes you a better doctor.
Of course, yes. Of course. And then you know that is using ultrasound machine or X-ray or kind of thing. You know how it works. You have more confidence in yourself. You're learning better. Okay? And those people, they put physics, they don't put it for this, And then I said, I will say that physics should come back next when you have in the 5th year of the college, That is something, but I don't think that. Okay. That is why people we don't need, no need physics. That is why I don't see people around here. Okay? Okay. Now, of course, that is, as I said, that is also, that is for spherical, it'd be what? There is 2 something in here, and that is missing in here, okay? So divide by 2 here, or 2 t's, So, as we say that is, I just summarize what I said all the way on. So I read that the tension of the walls of the container depend on both pressure of the container's content. Of a container's content could be blood, could be another thing. Later come back say that is how is velocity affected in it. Okay, and it is radius. These 2 factors, where we say pressure and R, is very important. Okay, and thus we say that is if you double the pressure, you double the tension. If you double the radius, you double tension. Okay, but what the pressure is equal to tension over R, isn't it? Yeah. So when you're using the R, pressure also increases. I just swap with the things, Instead we say T equal to PR, we say P equal T over R. Okay? Then you can see that is how is R changes with the pressure. Okay? Okay, I'm just telling you that is if you increase it twice pressure by 2, you get the tension is increases by 2 too. That is quite linearly proportional. Okay? So we don't have any, say, squared or something like this. Now we see that it's blood, isn't it? Yeah, contracting, relaxing, contracting, relaxing. Okay? The blood is coming out in the pulsated way. It's a pulse. Okay? When pulse comes to the artery expands. okay? And due to the elasticity, when the pulse passing by, the elasticity recalling back. So extending, coming back. Of course, extending, they let all the volumes going through. When you're relaxing, push the whatever blood left in the retina to go to the other downstream or to the other vessels and vessels, whatever is connected to. Okay? So basically that is, we say artery as an elastic rather not rigid. يعني. Rigid means that صلب يعني أنبوب خاص يعني من الحديد من أي شيء. Elastic, when they say elastic means that it can expand other things. We call this was compliance. You know. Okay, compliance allows to an artery to expand when blood is pumped through it from the heart and then is recalled back after the surge passed by. Okay, that is when I have my heart is contracting, I have blood coming to the veins and all blood vessels in here, but blood vessels higher probability they expand, okay? And because elasticity like rubbers we have, and it's coming back, isn't it, yeah? So you can push in the blood again through the other vessels, okay? This slide was telling you the thing that is a heart here that contracts the arteries going expanding in downward here, okay? When the things go by, then this is coming back to there. So when the heart is relaxes and stops pumping blood into the arteries, the stretched arterial walls passively recall back. Okay? ترجع مرة ثانية إلى هذا. So recall pushes the excess blood flow that contained in the artery into vessel down the stream, maintaining blood flow to the other, say for example, tissues and cells. Okay? Now, of course, this contracting thing is related to the blood pressure. Okay? So we can define blood pressure is what? A force per unit area on the walls, exerted by the blood on the walls of the arteries or blood vessels. Okay? So we're going to say it's a pressure exerted by or the force exerted by the blood on the walls of the arteries. Okay? When we say we're measuring pressure, isn't it? Yeah? We want pressure. What we do that is we can say, according to Pascal, so you put this cuff around, isn't it? Yeah? So what is happening? This is going up and down. We're going to close it, as I told you, yeah? And then open it. When you open it, that you have turbulent flow. And turbulent flow is make a sound. And the stethoscope, you're hearing the sound. And you know that is, what is it? Systolic pressure. Okay? Systolic pressure. And they will be watching this, listening to sound, and the sound is ceased. Then means that the turbulent flow is become what? Streamline flow. No sound. Okay? From these two things, you can measure what? Where comes the sound first, and when the sound is ceased, then you have the systolic pressure and diastolic pressure. Okay? So blood pressure is the force exerted of the things. Blood fractures fluctuated due to their elasticity. Of course, we say that this elasticity fluctuating and things. That is the elasticity make us to think. Actually, that is normal one with the cystoscopes. But also we have this more advanced ones, which is made ultrasound. So this thing is coming, or sound pick up that an ordinary or digital ones that you can see now, you can buy in the pharmacy, is sound. Is what you call it, سماعة. No, it's not because سماعة موجودة هنا. فهاي السماعة تسمع اسمه heart beat. Okay, when you see the heartbeat, it's got a signal. When there is no heartbeat, a signal, and then electronics will do business for you. Tell you what is the systolic, what is diastolic, what is your heartbeat. Okay, it's a more advanced one. It's ultrasound also. Okay, you put the ultrasound. When this is expand, you put the pressure. So you're producing a sound wave. when you go back sound wave. So again, تضاغط, yeah, is happening. That this would be the piezoelectric crystal pick up these things and you go make it electronics, digitals, and give you the values. Yeah. Okay. This is 2-3 types of the measuring the turbulence. Okay. Of course, as we say, that is black fluctuated, you know, and maximum pressure produced on the artery, we call it what? Systolic. And minimum pressure on the arteries, we call it what? Diastolic. Okay, that's just in word reason. But if you do fancy ones, okay, systolic pressure is the maximum pressure extent on the arteries walls when the blood ejected into them. And then we know that is normal person is 120 millimeter mercury. Yeah? And diastolic pressure is the minimum pressure within the artery when blood draining or drainage from them, which is about 80. So we know that systolic pressure is 120, diastolic pressure is 80. Okay? And this is due to the maximum pressure and due to the lower pressure. If you look at this picture here, which is about nearly, if you talk to the top here, is about 130. As I said, that is 120 is okay, but also 110 is okay, and 130 also is okay. So you have always plus or minus 10. Okay? So you're not getting everybody that's getting 120 or something, but the people who did the research in the beginning, they collected all of thousands of the people, and they did blood measurements, and all of them is coming out 120 as average, and then 80 as average for diastolic pressure. Okay? Now notice what is happening in here. If you look at that one here, if you read this graph, you know, what just note just for display, and what just to tell you how you drive the reading the graphs on the things. Okay, so if you look at that one here, then nearly that is the systolic pressure is about 180, and diastolic pressure is about 75 or 72. So the that you can read the things. Okay, and then we can read here this between these two in here. This is 0.5 and this is 1. Okay? This is what? 1 minus 0.5 is 0.5, isn't it? Yeah? This is a period. And we know a period, one of the period is what? Frequency. And frequency is the heartbeat per second or per minute, usually per minute. Normal people do about what? 60 something or 70, 75, say, beats per minute. Okay? Then if you read that one here, it's 0.5 second divided by 1 over 0.5, that is make a frequency, and 0.5 is second divided by 60, so 60 over 0.5 become what? 120. This is very hard beat in their husband. Most of the young children, they have more faster heartbeat compared to the young people. Okay? But that is just to tell you the graph, but doesn't tell you the exact numbers of them. Okay? And I just have you read them. Okay. Flow in rigid and elastic tubes. You know, really, that is not quite, title is not quite what we say here. You know. This is explain how you do qastara. Okay? Remember, we talk about aneurysm, isn't it? Yeah, we say aneurysm is wideness, isn't it? Widening of the vessel itself. Okay? But if you have a clot, say for example, this bit in here, okay, so it is a clot or plug or the deposit of the fats of the things in it. So just so you're reducing the diameter. Okay? Opposite to the aneurysm. When reducing diameter, what is happening? That is P, the pressure. Again, that is velocity increases because it becomes small, and then when velocity increases, pressure is go down, according to Bernoulli principle. P plus half rho V, isn't it? Yeah, rho is constant. Okay, density of the blood. So V and P. When we become small, like this, become small, okay, you can see that is very small, okay. When it becomes small, means velocity, according to continuity principle, velocity increases, okay. When velocity increases, according to Bernoulli principle, pressure is go down. When pressure is go down, my whatever vessels I have at this side in here and this side here need the blood to go. Or need blood, isn't it? Yeah, you need the blood. Your heart would have to supply blood to other organs through this thing, So your heart has to work hard because the pressure down in the upper to produce sufficient pressure to the blood go to the all parts of your body. When your heart is working hard, means that is the possibility of the heart failure is there. Okay? So that is the clot does. But how are you going to remedy that one here? Well, so by put a stent. Okay? And a stent, this is a stent like this. So you can a catheter, you have a catheter, and you put it step through, say, for example, some vessels in your thigh or somewhere close. The doctors will choose where it go start, okay? And you go to the region where you have a clot, and then a clot you can see that is through what technique? Ultrasound, isn't it, yeah? Yeah, well, from last lecture. Okay, so you can see that one through the ultrasound on other techniques and you can use. And then you put the stents in there, and then it's a balloon inside there. So what is happening with balloon inside? Explained the thing is better. So at the end it's become normal, its flow is going, blood is going through the flow freely. Okay? Now, I've been walking in the kitchen to find out this thing, to explain to you how the Laplace's law works. Okay? I forgot. Okay, so I'll come back to that one here. Now, I'm going to food that one happen. I hope there's no hole in there. Okay? If you look at that one here, radius is small here, isn't it? Yeah? Radius in here. Its pressure is constant because I put whatever it is. So Rn, tension with you. Look at the tension here. It's no tension because R small. And the tension here is how much? Okay, so we'll come on how R is related to the things. Okay? So that is the quite nicely explained what is the present for you. Okay. I would say it should come in the beginning of the lecture, but it's again, okay. And I would say, why spherical pressure vessels more efficient than the cylindrical ones? Actually, that is not quite, it's only bladder or heart or the things going there. So most of them, they are not spherical shape, okay? Pure spherical shape, you don't have it in body, okay? But we say that is, why is more efficient than the tubes, vessels, okay? Because what you say, the minimum surface area to volume, if you work out any spheres, it will be spheres divided by volume, you're getting minimum, okay? And then another thing that's according to Pascal's pressure inside the sphere is all the same in all directions, yeah? And the third one is the spherical symmetries. They are symmetries, so anything that is not bending like this sphere or the kind of thing. Okay, so it will be symmetry. So the pressure is all around, it will be the same. Unlike the tube, which has no symmetries. Okay, so that is why we think it's minimal. And again, that is red thing is in here. And then when you have on the sphere, you don't have bending things. When you have a road, so that you have bending, so a lot of the stress and shear should be at that point in here. Okay, pressure pushing down, you have to return it back, losing a lot of the pressure. So when you're losing those pressures, you'll be that you have what? You have to work hard on the things. Again, your heart will work hard. Okay? Now, you go to the last part, Pois's law. Pois's law is a French name, really. That is, everybody pronounces differently. Okay, so whatever you decide that the Pois's name is. Yeah. Of course, what this guy did in 1800 something, he got a tube. How can I just tell you, explain the experiment to make you understand better. He got a tube, okay? And then measure the length of the tube and then the diameter of the tube, okay? And then he put liquid going from here. Pressure is higher in here than pressure than here, so we have a flow, isn't it, yeah? And I put a beaker, simple beaker in here, and measure how many volumes got per minute or something, or per 5 minutes. So I got a rate, Q. Okay, flow. Okay, flow is the mass per unit time. Okay. So what he did that he said that is, first of all he said that pressure, the flow is depend on the pressure differences. It's quite bigger differences, say 100 or 50. Of course, 100 has more flow compared 100 differences compared to the 50. Yeah? Yeah? Okay. So, again, it depends also inversely proportional to the resistance R. And I notice R is let's say, let's say that complete experiment. So, okay, I have a pressure P2, P1 bigger than P1, so I have a flow, okay? And then I have the fixed L at this point in here, okay? So while we're going down, so the pressure, I have a fixed L. I can keep all this constant in here, and then you see that is how resistivity proportional to the L, okay? And I say that is, as the length is getting bigger, resistivity is increases, like electricity, okay? Smaller, less resistivity. In other words, that is, if I keep all those things constant, so R is proportional to the L, okay? Now, what you did that is, again, you bring what? Different liquids or different viscosities, okay? You know what is viscosity? Like water, isn't it? You're drinking water, it's less viscous. And then you pour water to the glass, it's much faster, isn't it, the flow, compare you put what? Honey. Honey more viscous, isn't it, yeah? So you put different materials on blood. I probably same blood and increases the number of the red cells in the blood, you can increasing the viscosities, okay? So I find out also resistance is proportional to the viscosity. Another thing that is radius also. He find the tube, a small radius, is proportional, inversely proportional to the R to the power 4. R to the power 4. If you look all those things in a linearly proportional, this is important factor, which is R. And R is 2 to the power 4. It's if you're reducing, say for example, increasing R twice, become what? Twice to the power 4, you said 2 multiplied by 2, 2 multiplied 4 times 2, 2, it becomes 16. Okay? So we go by 16. So R will be what? If you make it twice, R is go down by 16 times. It will be bigger, huh? If I make it half of it, 1 over 2, so it will be resistivity is increased by 16 times. You understand that, yeah? Yeah. Okay, so that's just the factors you play with here. So he find out with the thing, I don't know where is 8 he's come from, just a fixed number to make things right here. So he come out that is the flow is the pressure differences over this, which is coming back, would be pi over 4, 8 eta multiplied by L, length. That is would be what? A flow. Yes, sir. Hmm? Cohesion force, yeah. But this loads is in parallel loads, it's not calculations of kind of things. Okay, cohesion is viscosity. Okay? We understand where these things come from. Okay? So we're going to, if you understand that, the rest will be easy. Okay? Now we say that is for a flow of the blood in the blood vessel is delta P is the pressure differences between the two things. I should just repeat, I think. Let me go to the thing again. If I have a tube like this, okay, and the pressure is 50 and that one is 10, so the differences would be what? 40. So that is the depend of the pressure differences. If I have bigger numbers, it will be different flows here. Okay? Now, okay. Now we have 4 cases in that plan. So let me take case 1 here. Okay? Again, I have 50, 10, differences would be 40, isn't it? Yeah? I have a flow that much in here, whatever I collected per minute. Okay? Of course, that is considered that is R constant at this moment. Okay? No change in R. Okay? Well, R, viscosity, length, and radius also, all together here. And if I change this one, 90, 10 is the pressure is different, is 80 millimeters. You see that is more coming out in here compared to that one in here. So it means that the flow is higher. What I'm just telling you that this Q, which is flow, is proportional to the pressure differences. Okay? Okay. And this one is exactly the same thing. Even I have different values, but the differences is coming the same, but you have the same flow. Okay? So all these things are telling me that is the flow is proportional to the change in the pressure. What is happening if I have 10 here and then 50 at this point here? Where does flow goes? Which direction? Opposite. So these red things should become here. Okay? Now, I'm just telling you that it's important of the R to the power 4. Okay? Now we're going to see that this, I brought this here. You see, there are 3 primary factors in there, which is related to the resistance, which is eta, we call it viscosity. Some people, they say U, microns, things, but most of the time, it's eta. And the length of the tube and radius of the tube in here. Of course, of these 3 factors, the R is probably more important than others due to the factor of power 4. Okay, the factor of the power 4. Yeah. But also that is, as I said, the vessel length also has play a role, but it's not as much as the R. Also viscosity also play the role. So viscosity always will be the same in the blood. If you have a problem with the viscosity, then you need some kind of tablet you can thinner, isn't it? Yeah. So most of the people the old people, they have heart problems. They take aspirin, isn't it? Yeah, at night. So dilute the blood. We make it less red blood cells in there. So the diluting thing is not reducing red blood cells, but you can red cells swimming in the different plasma. Okay. Okay. That's the length. So we say that when the vessel resistance is directly proportional to the length of the vessel, that is why I told you that, and proportional to the viscosity, and inversely proportional to radius power 4. Okay? That is how you read that one here. Now, the Poiseuille's law, if I combine both of them, flow, which is equal to delta P over R, and the value of the R, which is related to the 8, isn't it, yeah? And viscosity, length, R to the power 4. I'm getting some kind of equation like this in here. Okay? Now we could say the pressure drop along there. So remember how this pressure drop, not pressure. It's when you bear pressure P2 minus P1 or P1 minus P2. Okay? Don't confuse between pressure. If this, whatever I say that, if it's only P, would be all story would be different. Okay? Pressure change, pressure gradient, you will say. Okay? Now, Now it says the pressure drop along the blood vessels increases with the increasing viscosity, as we say that. So the increasing length also, okay? This is the pressure. I have a long hose. شو تسموه انتوا بالبحريني hose؟ ها؟ صوندا احنا نسميها. Okay? Okay, so tube طويل مال حدايق. If you have long ones, isn't it? Yeah, your pressure drop is higher compared to the small ones. Yeah. Okay, and that is why the pressure drop along the vessel with the large radius is much smaller than the pressure drop of the vessel of the smaller radius. You know, to the power delta 4. Let me take one example again. Okay, then we say that is increasing the radius by 2. Okay, we know that it's 2 to 16 easier, and I had to go to 256 or something like this. Okay, so with 2. So I would say that increase by 2, 2 to the power 4 is become what? 16. So pressure drop would be increases by 16. If I reduce it to the half, okay, that one's increased, isn't it? Yeah, because it's bigger numbers under the thing, so become high. Okay, now we're going to take half, isn't it? Yeah, half is become 1/16, isn't it? Yeah, 16 is going up, so the pressure drops 16 times. So it decreases by 16 times. Okay, this is good for multiple choices. Okay, now of course that it's we look at the actually I leave that one here. It's just we say that is how it decreases with the radius of the thing. It's because I repeat it so many times now. Okay, you don't need that one here. Okay, now we move. Now, before I do that one, you go back to the something here. Oops, sorry. This note, yeah? Most of the pressures in the cardiovascular system, you don't have these things, you can write it down, yeah? Loss in the arterioles and capillaries because it's such large decrease in radius. Okay? And we later on display something to tell you the things. Now, we talk about length, isn't it? We talk about the radius, and then we talk about viscosity. What is viscosity? Resistance to the flow. That's the simple thing is in here. But when we do fluid here, I have a layers of the fluid coming. This is one layer, this another one, and another layer. Is the friction force between layers of the liquid when one passing on each other. Passing over each other. Okay? So let's say that is if I have a tube, then you have a friction and this wall is more compared to the one in the next layer and next layer. At the end, you got what? Velocity profile. And velocity profile in the middle of the tube is highest velocity. When you highest velocity means what again, Bernoulli? Pressure is low. Okay, so what is happening is when the pressure low, then the flow would be different. Okay, but again, remember those Ronaldo, all those things, you know, Messi, Ronaldo's, yeah? They have a ball and hitting things up, it's going to the hole, to the goal, yeah? This is Magnum effect. Like in physics, yeah. If it's the same, this red blood cells is moving with the same direction, they have a force going that direction in here. So this process is happening in the blood vessels to keep red blood cells in the middle. Doesn't go to the branches, you know. So most of them would be due to Magnum effect, would be in the middle. Okay, so the viscosity, we say that this is the frictional force between adjacent layers of the fluid as they move past one by another. Okay. Of course, viscosity is temperature dependent, isn't it? Yeah. When you increase the temperature, viscosity is go down, isn't it? Yeah. When you have to have something you want to pour quickly honey, isn't it? Yeah, you heat it up a little bit to become less viscous, okay, more flow. Okay. I would say the resistance is caused by the intermolecular frictions, or just different. But the simple way is the resistance to the flow, friction, and then you go more details. I don't know why the three of them, why intermolecules, how they reacting with each other. Okay, so you have a macroscopic, macroscopic, and microscopic things. When you're talking about molecules, other things. Now, in the blood, what is the reason for the viscosity? In the blood, so viscosity is number of the red blood cells. So we're going to say the number of the cell viscosity increases by increasing the number of the red blood cells. Okay, when you have a large number of red cells, you have the viscous blood. Okay, so we say that is the viscosity of blood mainly due to the presence of the red blood cells. The suspended cells exert a frictional drag between them. What do you mean a drag? That is one of them pushing down, is going to the flow, moving, as you say, let's say, collecting in the middle or not. So the number of the cells increases, apparent viscosity is increases also. Okay, so these things we call it by hematocrit ratio. Have you heard about hematocrit ratio? No. Hematocrit ratio is a test people did it they do in the labs, all the things, to see that people suffering from anemia or not. Okay, anemia is this red blood cells in your blood. Okay, now, so what is hematocrit ratio? Is the ratio of the volume of the red blood cells to the ratio to the whole your blood or to the plasma. So basically what they do that is take a sample, quite easy, and then they put in the test tube, okay, yeah, and then you put it in the centrifuge. Centrifuge rotating. So that is the heavy one is go to the bottom, and the platelets would be at the top, and white one, and the platelets would be at the top. And then you have a plasma is floating, isn't it? Yeah. So the ratio of the whole to the one you have with the red cells, they give you hematocrit ratio. If I forgot the number, but if you would certain numbers, you are okay. If it's below this number, you have anemia. That is one thing. So people testing for anemia, and then it's also that's to the viscosity. Higher hematocrit ratio is higher viscous the blood is. Okay? Which one direction? Okay. Endothelial glucoglax. It's some kind of the glucose. It's some kind of the material is what you call the covering laminin of inside laminin, that's out of the word, yeah, of the tube itself, of the vessel. Okay, has a few functions to that one here. One function is increase permeability, okay, to food go out of the capillaries or kind of things. And the other one would be what? Reducing what? Friction. Okay, reducing a friction. So that is discover things here as well. So that is capillaries is glucose layers endothelial cell surface plays critical role in modulating the nearward movement of the red blood cells here. Okay, so let it go, dragging, all the things, but overall reducing the friction. In our case, and this is again revisiting velocity of the blood flow, viscosity, and blood flows. Again, the title not that much fitting the thing, but again, we are visiting again continuity principle. Okay, we're visiting continuity principle, and continuity principle we say that is velocity inversely proportional to the just different writing, yeah, with the cross-sectional area. Okay. Now, as I say, that is when a cross section is getting bigger, velocity increases. When it becomes small, when it becomes big, velocity decreases. When it becomes what? Small, velocity increases, inversely proportional. Okay. Now, if you look at this picture in here, again, this is we can explain as aneurysm again, or just widening to see that is in this case that is see that is a real system, that is venous system, that is bringing blood and then taking blood back to the heart, and then in between capillaries. And capillaries, you can use this simple equation. We say Q equal to Q2, okay? Velocity A1 is equal to velocity A2. If I find out in one capillary, say in the vessel, in the artery, this is cross section, and that is velocity, and then in capillary, that is the cross section, and that is, but that is the cross section of the capillary and velocity in the capillaries. But capillaries is not one, it's a number n. So I put in air and then put plugs of the things. You can go with about millions of the capillary you can find out in your body. So you represent all million capillaries of the bit here. Okay? This hair, okay, represented that one here. So we're not taking the cross-section area of one capillary, we take the cross-section all together. Because what is feeding, isn't it? And the coming here is gone there, it's gone there. If you find out one of them, it's very difficult to come, or we can do it when you do research on the things in it, okay? But that's just where we can have it. So again, when it's become bigger, cross-sectional area altogether in the capillary is much bigger to the arteries, isn't it? Yeah. Okay. So if you cross-sectional area A1 and this cross-sectional area A2 here, so A2 is much bigger compared to that one in here. Okay. So when you're bigger means the velocity is small, isn't it? Yeah. When velocity is small means the pressure is also high at this point in here, according to Bernoulli principle again. Okay. Well, what is all just telling you how you see that is the flow going through the capillaries and arteries and other things. Remember? Yeah, cross-sectional area of the things. So we say that is large artery, small artery, arterioles, capillaries, venules, veins. Okay. Now, if you do all these things similar, if you take this, say for example, this is representing what? Cross-sectional area, this brown one, okay? And they say that is, of course, that is getting a little bit larger here, something like this, and it doesn't matter really for us, but they see that is the total cross-sectional area. It's much bigger compared to the cross-sectional area. You see that one here? Okay, that is a capillary corresponding to that one here. Okay, that is veins and venules and veins and other things in it. Okay, look at this one here. The reddish color in here. According to the continuity principles, is the cross-sectional area is going big. What is happening? Velocity is go down, isn't it? Yeah. So that velocity centimeters per second. So that is when it become high. Conclude. The velocity in the artery, in the capillaries, is much smaller compared to the arteries. Okay, due to the cross-sectional area. And you say that is due to the change, this is the blood pressure in here. The blood pressure in millimeter mercury here, the blue one is in here. Due to the change of the radius, we say that is most of the drops in it. So that is the arteries, is in the small arteries. Small is coming out, changing, also going up and down in here. But when they're coming from the arteries to the arterioles, the pressure is dropping quite significantly. Okay? No. We're not, this pressure, we're not talking about it. We're just talking about the R small here. Okay, when you're going to see that the larger area, larger area here, see there's more drop in here. Okay? Again, you go back to the write it down, Bernoulli continuity principle, Bernoulli principle, and the Laplaces, if we look at the tensions. Okay? So cross-sectional area, again, bigger velocity here, small pressure should be low, high. And that is we're talking about the things like cross-section. Huh? Red line, yeah, on the red line. Not orange. Orange is the capillaries, and red is the velocity in the vessels and veins of the circular system, and this is the pressure drop of the things. As I say, that is most of the cardiovascular is arterioles and capillaries because of there's such large decrease in the blood vessels in here. This is more things that is represented the red ones, in the previous slide. And we can say that is here, this is heart beating, isn't it? Yeah. Okay. And if you look down heartbeat, that is the maximum is B120, that is systolic pressure, and 80 is about diastolic pressure. Differences between this, we call it what? Pulse pressure. Okay, so that is the pulse pressure between 120 minus 80 is called what? Pulse pressure. Okay, and this is represented. And then the average, remember that we say average 120 plus what? For arterial, 120 plus 80 divided by 2, this is average, yeah? So that is only going, at this point, average is nearly about 100, okay? Not quite, because what we're going, people getting from internet, let's make the expanded things, so numbers will missing the thing. But the average is 120 of the things in here. Okay, you can measure main pressure, things, all the things. It seems to be Dr. Waheeb not covered it here. Okay, again, the same principle here. We're just repeating it. The cross-sectional area is getting bigger, and then what is happening? The velocity is going down. Okay, so as I say, that is the lowest. This is same thing really. That's okay. So what we learn from there, we say that is due to the R to the power 4, pressure is dropped in the arteries and capillaries more because of the proportionality to the R to the power 4. And then when you have a cross-sectional area is big, when the velocity is low. So in capillaries, velocity is lower compared to the arteries and arterioles. Okay? An example, we don't have that one. You can take a picture. Take picture, me with it. Okay. A blood vessel has a radius of about 1.5 10 to the minus 3 meters. It's 1.5 millimeters, yeah? And the blood flow at the rate of the, you see, the blood flow at the rate of about 1 10 to the power minus 7 meter cubic per second. This is volume, isn't it, yeah? Meter cubic. Through the vessel. Determine the pressure gradient that must be maintained between the two ends of the vessel. We need pressure gradient, isn't it, yeah? What is pressure gradient? فرق pressure, isn't it, yeah? What's فرق pressure along what? I brought this question 10 years ago, something like that. So all of them, they didn't know it's pressure gradient. Okay, so I brought that one to make you what's the pressure gradient. Pressure is a fall of the velocity gradient, isn't it? Yeah, the velocity change over the time, okay, or velocity change over the distance. Okay, gradient is the pressure drop along the tube. So if you look at that one, most of them say that there's no L in here. There's no value of L. If you look at the here, I have this one here. I have viscosity, no L. I have R also, isn't it? Yeah. So delta P over L is the pressure gradient. the change of the pressure over that length. Okay? So that is what, at advanced, you can plug all those things, and the answer would be that thing. But the result is coming out in pascals. Yeah. Okay? But he asking you to change it to millimeter mercury. How you change it by millimeter mercury? Remember magic numbers, I told you 133? 1 millimeters equal to 133. So that one, we can use that one here to change it. Otherwise, you have to find density of the mercury, G to the gravity, and height, how much is millimeter. And millimeter converts it to the meters, and then you convert the things happening. Okay? If you don't forget that one, and you have a pressure is coming out, isn't it? Yeah? We have a pressure come out. So the pressure, whatever pascals in here, is equal to rho GH, yeah? Rho density of the mercury, which is 13 something, yeah? And G, we know the G, 9.8. And rho, this is H, we're looking for it, and we find out what is H, and then we say that it's that much millimeter mercury. Okay? But if you know this number, that would be fine. Again, you take picture one and you answer yourself, discuss it. Okay? Then it's telling you that you understood all the laws we talk about it. Yeah. Okay? I'm sorry I go out a little bit of the things, but I won't. How much I know, I give it to you, if I remember. Yeah. Okay? Because what is happening at the end, I coming to hospital, I need you. I want you to be good doctors. You know. So. Okay? Any question? That's just the last, I think, the last, yeah? I was doing some fancy things, you know, to explain things. Oh, it didn't work. Yeah. Anyhow, you can, this too, let me go back to here. You can take those things telling you from these laws which one is right or not.